4.2, we started this section last time. Remember, it was a continuation of 4.1. We're talking about these different numeration systems, and the one that we left off on was the Babylonians. The Babylonians had these two symbols, and these two symbols were repeated until you get to 60. And once you hit 60, then they're not going to be repeated. They're going to move into a second place value, and that place value is going to be the 60s place. Okay? So I want to remind you just where we were. These were our examples where we took their numerals and we turned them into ours. Every time we have a smaller numeral, that's the triangle shape, followed by the larger numeral, the arrow kind of shape, that's when the place value changes. So I drew in those vertical lines to show where those place values were changing. We figured out by counting pretty much how much each of those were worth. And then we multiplied them by the place value's value, right? We're in the 60s place, we multiplied by 60. We're in the ones place, we multiplied by 1. Or we just didn't multiply by anything, if you think about it that way. It continues on, so we have 60 and we have 60 squared. So our second example here actually was the 3600, or the 60 squareds place. Now the question that we left off on, and I had gotten a couple of you sending me questions about it, and I just said, hold tight, we need another example. We've only seen one of these, was turning one of our numbers into one of theirs. So this requires what I call a division algorithm, okay, or a division scaffold. But we've got this sort of like ladder of division going on. It's a ladder is what it looks like. And we start by taking our value that we're given, so that was our 3280, and we wrote it underneath a division that looks like it has sort of a division piece on both sides, right? Almost like a house. So the number we're dividing by goes on the left, just like it would always. And on the right-hand side is how many whole number times it goes in, and your calculator assists with that. So we found out it was 54. Then we multiplied the 54 by the number on the other side. So we end up doing this sort of multiplication process right here across, and that value goes underneath. So 54 times 60 was 3240. We wrote it underneath, and we subtracted. When we subtracted, we got a 40. And then we did the same thing again with one place value down. So we went from the 60s place to the ones place. The ones place is not very exciting, but it's easy, right? The number 1 goes into the number 40 times. 40 times 1 is 40. We subtract the 40, we get a 0. So these numbers that we get at the end, 54 and 40, tell us what we draw. So 54 is 5 of the arrows and 4 of the triangles. And then 40 is 4 of the arrows, and we're done. Okay, so that's where we left off, and we're going to do another one, a slightly larger value. It's 43,205. So taking a look across the top of my place values, I have the ones place, the 60s place, 60 squared, which is 3,600. 60 cubed is 216,000. I need to use the one that's the largest, but still smaller than 43,205. So what number am I going to divide by first? 3,600, right? 216,000 is too big. So I want to do 3,600. So I'm going to draw my division hat, right, like this. You know what? Let's use the white. So I have 43,205, and I'm dividing by 3,600. And if you grab your calculator, that's how we do this part. So we need to know how many whole number times 3,600 will go into 43,205. What's your calculator tell you? 12. Thank you very much. Everybody's quiet today. 12 is the right value. And then if we take 12 and I multiply it by the 3,600, right, with multiplication, what will I get? 43,200 even? Am I hearing that right? Okay, great. So if I subtract this, what am I left with? 5. Now, what I'm going to do next is not going to make sense in terms of this problem, but it's going to help us when we get to 4.4 to have done it the same way. So bear with me on the fact that it looks like I'm doing an unnecessary step, okay? What we're going to do is we're going to divide by one place value down from 3,600, and that number would be 60. And the reason it looks silly is because it doesn't go into 5, right? That's okay. It's the number 0. 60 goes into 5 0 times, and we subtract the 0, and we just move along the process. And it will be clear when we get to 4.4 why we just did that. For the moment, it seems rather unnecessary. Now, we keep going down in place value. We did 3,600, we did 60, now we're going to do 1. 1 goes into 5. 5 times. 5 times 1 is 5. And we get a 0. So we are done when we've done our division by 1 and we've gotten a remainder of 0. Those are the things that tell us we're done. Okay, so we need to do our Babylonian numerals now for the numbers 12, 0, and 5. So how do I write the number 12 in Babylonian?
The arrow thing and then 2 triangles?
An arrow and 2 triangles, you got it. What about that 0? There's nothing we can do, right? So we rather ignore it. We're going to come back to it in a minute. And then how do I write the number 5? 5 triangles. And you might see even these 5 triangles. That wasn't good. Let's try that again. Running into the other 2. Now, I choose this example on purpose to show you that there's a problem with this. In fact, there's 2 problems. The first problem is the 0. Best case scenario, if I looked at this and I said, where does the place value break? I might break the place value here. And if I did, and I didn't know there's a missing place value, I might think that this is the 1's place and this is the 60's place, right? And if I did this and I worked backwards, like we did in those other problems, I would not arrive at the number 43,205. Think about how the accountants had to keep their books to make this work. Right? If somebody owed you money, but we're talking about the Babylonians, so maybe it didn't look quite like money, but they owed you sheep. They owed you 43,205 sheep. How do you write that so that it's very clear that that's the number instead of it being 60 times the 12 and 5 times the 1? They didn't have a way to do it. It just didn't exist. Even worse than that, they might have not even understood that this right here was separated. These might have sort of been more run together like such. What would be that number if it was all mushed together? 17. 17 is way different than the number 43,205, right? Okay, so I don't bring this up to try to make you think, well, what do I do in the test then? Or what do I do in a quiz then? Or what do I do in a homework then if there's this ambiguity? There won't be ambiguity on the ones that you guys are dealing with. But the reality in this number system is that there's a lot of ambiguity, right? There's problems that are existing here that we can't fix, and probably lend a lot to why we don't use a system like this today, right? Our next system solves one of these problems, but not all of them. They're the Mayans. You've probably heard the Mayans before. What are some things that you know about the Mayans specifically? They're credited with quite a few things. What's that? The temples that they build, some of their architecture. Babylonians are actually credited with architecture too. So do you know where the first Babylonians are mentioned in history? Genesis. What's going on in Genesis with the Babylonians? Nimrod. Some of you are like, who's that guy? He's after him, yeah. If you're familiar, you probably would remember it being called the Tower of Babel. That's Babylonians. So these are very, very old societies, okay? All right, so the Mayans are not quite that old, but they are credited with a lot of their architecture, just like the Babylonians actually were too. What else do you know about the Mayans?
They do like human sacrifice stuff.
They probably did do human sacrifice stuff. That's not what I was talking about, though.
Funny headdresses and stuff.
Funny headdresses. How about calendars? Do you remember the Mayans and the calendar stuff? 2012, the end of the world was supposed to happen, right? 2012, we're still here, it's 2023, it didn't work out that way. Maybe they didn't even mean that, maybe they just stopped writing out the calendar, we don't really know. But there's a calendaring thing. This is actually a very advanced society for the time, very advanced. So in their system, they had 3 symbols. The symbols represented the numbers 0, 1, and 5. Okay? The 0 symbol is the most interesting, and at least we have one. The Babylonians didn't have one, right? And we saw the problem that caused. So the symbol that they use, again, this is another one that looks different on the different resources I teach out of, so I want to make sure I draw it the way that's most similar to yours. Looks something like this. Okay? It's usually called a shell. I think it kind of looks like a little loaf of bread. Right? The others are really easy. 1 is a dot, and 5 is a horizontal line. So this society wrote their numerals vertically like the Chinese did. We did that back in 4.1. Okay? Smallest on bottom, largest on top, so that part is the same, right? I mean, it has the same sort of verticalness to it that we were talking about. Smallest on bottom, biggest on top is theirs anyways for the Mayans. They have a modified base 20 system. So when we did the Babylonians a moment ago, we talked about the fact that they had a base 60 system, right? It was all powers of 60. The Mayans didn't have all powers of 20, but they had mostly powers of 20. They have this very interesting thing right here that they say that instead of doing 20 squared for their second place, they do 20 times 18. Somebody figure out what 20 times 18 is for me. Because there's a reason. They didn't just arbitrarily choose this. What'd you get? 360. Why might they have chosen that they really wanted their next place value to be 360? Say it again. It's really close to the number of days in a year. That's exactly why they did it. Now, why do you think that they chose base 20 to start with, as opposed to say we use base 10? We use base 10, they use base 20. Any idea as to why? Why either of those are the way they are? So we use base 10 because you have 10 fingers. So why might they have used base 20?
Fingers and toes.
Fingers and toes. They're not wearing these little closed-toed shoes like well, maybe not all of us have them today, but, right? They're not using closed-toed shoes. They're fingers and toes, right? Like, this makes sense. So 20 seems like a reasonable number system to work with, whereas for us, 10 is reasonable. If God had not given us, if we look like Fred Flintstone, do you guys know who Fred Flintstone is? Okay, and most cartoon characters do this. They don't give them 4 fingers. Have you seen this before? How many fingers do they have? They have 3 fingers and a thumb. Go looking at it. Most of your characters in television, old school television shows, 3 fingers and a thumb. If that's what you had literally been given, and we'd all been given that by God, we wouldn't use a base 10 system. We'd use a base 8 system. I can pretty much guarantee that. That's why we do things in base 10, okay? So they're using base 20 for that reason. All right, their system is positional, much like we saw in the Babylonians, where it repeats within the system. So we're going to do an example. We're going to see their system written, and then we're going to go back the other way, just like we did with the Babylonians. Okay, so they put the dots on top of the lines. Write that down. Dots go over lines. Okay, so it's smaller symbol on top of the larger one. The dots over the lines tells you that when you change from a line to a dot, you change place value. So where I've drawn that yellow line through, that's a place value change because it went lines and then it went to a dot. Okay? Now, looking above my yellow line, I have a line and 4 dots. How much is that? Nope, close. 9. The line's worth 5. Remember the line's worth 5? Over here, right? And the dot's worth 1. So we have 5 and we have 4 ones. This is a 9. How about below my dot lines? I have 2 lines and 4 dots. That one's my 14. And maybe that's the one you were looking at when you said 14. Okay, so we have a 9 and we have a 14. This is not the number 914. Okay? The reason it isn't is because in this place value system, this is the 1's place, and then this is the 20's place. And if we move up from there, we have the 20 times 18's place, and then we have the 20 squared times 18's place. It goes in order of what's written over here. Okay? So we end up with 20, or sorry, I'll do it the other way. 9 times 20, and 14 times 1. So you can also sort of imagine, what if we didn't have all of the bills we had? No 5s, no 10s, and we only had $20 bills. Okay? So this is telling you have 9 $20 bills, and you have 14 1s to make this work. So we're going to multiply. What's 20 times 9?
180.
180. So 180 plus 14 would give you 194. Okay. Do you see the fun shape in the middle of our next one? Oh, we've got a place value holder. That zero's in there. It's great. Now the zero holds its own place value, which means that we actually change value both above and below the zero. We're also still stacking dots on top of lines. So there is one more place where we change place value. Where is it?
With the other dot below the, I don't know.
Okay, so is it above or below the zero? It's below the zero, and it would be right here. Dots go on top of lines. So that's a location where the line looks like it's on top of the dot. That's a place value change. So we're going to start at the top above my first vertical yellow line. So right here, what do we have? 17. How about in between the next two lines? That's a 0. How about in between my next two lines? 5. And then at the bottom I have 6. Okay, everybody good? Okay. I'm going to write in the place values next to them. So we start at the bottom. This is the ones place. Written, the bottom number is the smaller value, written on the bottom. The 5 on top of that is the 20s place. And then we have 20 times 18, or if you want to write in 360, you certainly can. And then what happens after 20 times 18? Right, 20 squared times 18. So we're going to take 17 times 20 squared times 18 plus 0, not very exciting, which is the 20 times 18, plus 5 20s plus 6 times 1. Sorry, I'm going to slide that over. It's kind of running off into the lighter color. It's harder to read. There we go. Do you know what 20 squared times 18 is? Does anybody have that number?
7,200.
It's 7,200. So I'm just going to take one step to write a little bit more out. You don't have to do that. I'm sorry, you said 7,200, right, Madison?
Yeah.
Okay. This is 0 times 360. Or you could just write 0 at that point. If you'd like to multiply things at the end, you could. 5 times 20 is 100, and then I have a 6. All right. So we're going to multiply 17 times 7,200. What does that give us? I don't have this written down at all. Somebody's got to help me. 122,400. Does that look okay? All right. Next one's 0, and then I have 106. So I need that 122,400 plus 106. What do I get? Fabulous. 122,506. That's better. Any questions on that? Okay. Now we're going to go the other direction. Okay. So we start with one of our numbers and we turn it into theirs. That's going to be a division ladder. So we have our number, 208. I'm going to write these down actually a bit. I have the ones place. We had the 20s place. We did 360 a minute ago. Madison told me it was 7,200. What would the next one be after 7,200? You multiply by 20 to get the next one because it's base 20. That's 7,200 times 20. 144,000. Sorry, I won't put the commas because then they look like the commas separating my numbers, but 144,000. That's probably as large as we need to worry with. I don't think you're going to see anything bigger than that, but those are the place values. So when we take a look at the number 208, I want to divide it by the biggest thing that I can that will go into 208. What will I divide it by? What was it?
60.
Did you say 60?
Yeah.
We don't have a 60. That's in the Babylonians. 20? 360. Which one? 20 on this one. Yeah, so this one will be 20. Yeah, if it were Babylonian, 60 would work, but we don't have a 60 here. How many times will 20 go into 208? 10 it is. And then we do the same thing we did before. We multiply, right? So 10 times 20 is 200. And when I subtract, I get 8. And what will I divide by next? 1. 1 goes into 8. 8 times 1 is 8, giving me a remainder of 0. So these numbers over here, 10 and 8, do not make the number 108. Can't tell you how many times I see that. It happens all the time, right? We have to take the 10 and the 8 and we have to put it into their numerals. So how do I draw a 10 in Mayan? 2 lines. I'm going to do mine underneath. 2 lines. How do I draw an 8 in Mayan? 3 dots in 1 line. What goes on top? The dots. So I do 3 dots and 1 line. That's really long compared to my other lines. We'll go with that. This is the Mayan equivalent of our number 208. Yes?
So I'm kind of confused on why would you put the dots on top of the lines? Is it because you're breaking up numbers?
It's because that's how they did it. They always did dots on top of lines. Like that's their system that they created.
Like the 3 dots, why wouldn't they go on top of the 2 lines?
Because that would actually put them with the 2 at the top and we'd have the number 13.
Okay.
We need to make sure that when we write these, that the top number here represents the first value, which was our 10, and the bottom one represents the number 8. So they have to go in order separately. Yeah. Okay. Any other questions? Let's try one more then. I have the number 58,532. What is the biggest value that divides 58,532? 7,200. All right, so we're going to divide by 7,200. And none of us are doing that in our head.
8.
Does it go in 8 times? Did you just do that in your head? No. Okay, just checking. Whew. All right, 8. Goes in 8 times. Remember, we're multiplying. What is 8 times 7,200?
57,600.
Okay, so we're utilizing our calculator for all the multiplications we need. That's all good. What will I divide by next? Oh, I didn't subtract yet. Let me subtract. What will I subtract? When I subtract, what will I get? 1,100 what? Can't be 37.
Why did I do that too? I misread my own handwriting.
I don't even think I have this one written down. Let's try the subtraction again. Is it 57,600?
I get 932.
932? Okay, yep.
Why would we start with 7,200 and not 44,000?
We don't have a 44,000. We have 144,000.
Oh.
That's why. But if we did have a 44,000, we would. You're right.
It's like a bracket.
Oh, sorry. It is the number 144,000. Good asks. You guys are clarifying things. That's really good. Okay, 932. I think 932 looks right. Does that look okay? Okay, what do I divide by after the 7,200? 360. How many times will 360 go into 932? 2 times. What is 2 times 360? 720. Mm-hmm. What do I get when I subtract that? 212 is right. What will I divide by after that? 20. How many times will 20 go into 212? 10. 10 times 20 is 200. When I subtract, what will I get? 12. What will I divide by? 1, which goes in 12 times and gives me a remainder of 0, right? Okay, that's all the math part, right? Everything else is transcribing into their system. So we need to take these 4 values in order and draw what they need to be drawn, how they need to be drawn. Okay, so how do we draw the number 8?
Line 3 dots.
Okay, how? Like, let's go from top to bottom.
3 dots.
Good, okay, there we go. So we're all make sure we're drawing the same thing. 3 dots, and then 1 line makes the number 8. How about the number 2? 2 dots. All right, the number 10. 2 lines. And the number 12. 2 dots and 2 lines, and this is 100% correct, but do you see a problem Even though they've got a 0, thank you Mayans for bringing us 0, there's still a problem with what I just wrote.
How would you know?
Kyle.
There's no break between the two dots and two lines.
There's not, right? If we were drawing in our natural breaks to this, we would draw them in right here, wouldn't we? How in the world would we know that there's really supposed to be one here? And even if you think maybe they need a space on there, like there's some distance or whatever, how much distance would you need to know it? 0 won't work. Because if I put a 0 in, it will hold a place value and it will be worth one of the powers of 20. It's not supposed to be worth a power of 20, right? I don't have 0 20 squareds or 0 20 times 18s. I don't have a 0 in one of the place values itself. So it doesn't help us. So again, is it going to show up anywhere on your stuff you're going to do? No, it's not. You're not going to have anything where they're tripping you up with this stuff. But I do want you to see that there's flaws. And because of the flaws, it's why these number systems did not persist. Okay? All right.